In this video, we will explore the implementation of the puck damage model in Abaqus, enabling you to predict damage in composite materials based on the puck criterion. Since the puck criterion is not included in the Abaqus material library, a subroutine is required. Depending on the problem conditions, different subroutines can be written to incorporate the puck criterion in Abaqus.
Here, we have discussed how to write the UMAT subroutine for solving problems using the Abaqus static solver, while ViewMat and USDFLD are covered in the package mentioned in the description.
Hello everybody and welcome to our new video training package of Abaqus, simulation of composite puck damage in 3D continuum element. Do not close this video, maybe it is your missed solution. By the end of the package, you feel like you have a solid understanding of the fundamentals of writing UMAT or ViewMat and USDFLD for modeling puck damage criterion. You're able to tackle your project with confidence, knowing that you have the knowledge and skills to success.
The question might arise, what are the differences between these three subroutines? The difference between UMAT and ViewMat is that UMAT is used with the static solver, while ViewMat is for the explicit solver. Regarding USDF and UMAT, both are used for the static solver. However, UMAT involves more complex coding, but you don't need to define the reduced stiffness values in Abaqus. Instead, you can define them in the code. In contrast, USDFLD has simpler coding, but you must manually define the reduced stiffness values in the Abaqus Material Properties table. Choosing the right subroutine depends on your problem requirements and coding skills. In the package mentioned in the description, we provide a detailed explanation of all three subroutines. However, this video focuses only on UMAT, with more details available in the package linked in the description. Let's start.
At first, we want to talk about the puck criterion. Two different types of failure or fracture are considered: interfiber fracture or matrix cracking and fiber fracture. The most noticeable difference between this criterion and the ones proposed by Hashin is that three modes of matrix cracking are considered, differing in the angle between the fracture plane and the lamina, as well as in the type of load, which causes the fracture as shown in the figure. A is a schematic of action plane concept and the definition of acting stresses on the fracture plane, whose angle is denoted by theta Fp. B is the schematic of the exposure fracture Fe, where Fe is the exposure factor at the failure point. The interfiber failure criterion is only a function of the stresses acting on the fracture plane. If the normal stress is positive, this equation can be used. And if it is negative, we can use this equation. In the equations shown in the previous slide, there are parameters that need to be calculated. Some of them are the failure resistance normal to the fibers or the shear resistances. The parameters presented before can be calculated by using these equations. We are going to test the UMAT subroutine with Abaqus solvers. In this part, we use the UMAT subroutine and we simulate it again with the puck criterion result. So open Abaqus CAE. As you know, the first module is the part module, and our model is designed here. This subroutine is for the standard solver. Also, these models are more for identifying the damage initiation. And whenever damage occurs, the properties suddenly reduce and the material fails quickly. Now we are going to compare different criteria to identify the damage initiation. In Abaqus, there are TSI-WU, TSI-HIL, AZIZ, and Hashin criteria by default. But there is no place to define a POC criterion. With subroutines, in addition to modeling the composite in 3D, we can also define the POC criterion for it. Let's start it. As you can see, our model has volume, but the standard and explicit models do not have volume and are shells. In the feature, you can see the solid option. In the property module, we can define the number of state variables we had in the UMAT code. Here in deepWAR, we can select deepWAR from the General tab. Here we specify the number of state variables. If you remember, we had 5 state variables, so we set this value equal to 5. This option is also for deleting the elements. That is given in the new version of Abaqus for UMAT. In the previous version, it was only for VUMAT, but we don't need this option now because we didn't have anything about it in our code. Now, if we want to define the mechanical and strength properties of the composite, we use the User Material option from the General tab. In our code, we had props as inputs. These values are the same as props. And also we use the mechanical option for this material. Moreover, you need to use the composite layup tool to create the composite layers. All settings are the same as before, except when you click on this tool, you must select the solid option instead of shell. Assemble your model in the assembly module and go to the step module. In this module, in addition to choosing options related to stress, strain and displacement as before. In State Field User Time section, we choose SDV for our state variables, so that all the state variables that we have defined will be displayed in the results. Also, we choose integration points for element output position. In the load module, as you can see, the model is fixed in the X direction from the left side. And there is no movement in the X direction and no moment in the Y and Z direction. The displacement is applied in the X direction to the right side of the structure in the amount of -0.2 millimeters. Applying mesh in the mesh module, and the element type would be C3D8R. In the job module, we select the desired analysis and wait for it to run. Now we want to explain the code of this subroutine line by line. We display the code using Visual Studio software. Here are the notes written in the form of comments by default on all the subroutines of our package. And after this part, our subroutine starts. As you know, at first, all the parameters and variables in the code need to be introduced. In the first part, the parameters to be calculated during the code are defined, such as stress, strain, or Stephan's matrix. Note that we have to calculate all these parameters and these are not inputs. The size of these variables is also defined here. For example, a 3D elements stiffness matrix is a 6 by 6 matrix. Now, in this part, we define the inputs we have. The values of these inputs are fixed and taken from the reference. For example, mechanical properties such as Young's modulus or shear modulus are among the inputs. Now we enter the main part of the code. At first we define the values 0 and 1 in this way, so that they can be entered in this way whenever we have them. In this line, a parameter called ETAV is defined. In the following, we will need this coefficient to reduce the properties. It is a constant value that is extracted from the reference. Now we want to define the input we mentioned before. For example, Young's modulus in the matrix direction is equal to props 2. Or Poisson's ratio in plane 1, 2 is equal to props 3. Finally, all variables used in the code are defined here. Here, prop 7 means tensile stress limit in fiber direction and is denoted by xt. And these are the parameters related to the selected criteria. In this training, the criterion is the PUC criterion. Now we take these inputs out of the comment mode and give them to the code. After that, we must define state variables. The first one is about failure in fiber, and its value is saved in state V1. For damage in the matrix, its value is saved in state V2. Note that in all the code we show these values with F1 and F2. The meaning of state V3 is criterion for fiber in tension, and state V4 means criterion for fiber in compression. The state V5 is for matrix failure. And we introduce these values from line 130 to 132. Now we apply the PUC criterion conditions in this code. If these conditions are met, we can calculate the value of the initial stiffness matrix. As you know, the dimensions of the stiffness matrix are 6 by 6. So here we consider its value from 1 to 6. Therefore, the C-full matrix is filled with the values of K1 and K2. And its value is equal to 0. All these formulas that you see were obtained by the help of Hooke's law and the relationship between stress and strain. For example, the first component of this matrix is filled by the value D1111. Now we can calculate the amount of stress using Hooke's law. In the next step, we calculate the values related to DDS-DDE. In the following, it is necessary that we check various conditions according to the PUC criteria. Our first condition is that if the value of F1 is not equal to 1 and also the value of sigma 1 is positive, we can calculate the FFT value. The formula written for FFT can be obtained from the reference of this tutorial. Here you can see it for positive sigma. If this condition is met, the damage number can be calculated using this formula. And we can call it FEFFT. And this is the formula of FEFFT in this reference. And again, due to the change in mechanical properties, we must recalculate the value of the DDS-DDE matrix and the stress value. Do not forget that these values are calculated with new mechanical properties. And now we have reached the end of this code. But before running, we need to select the path where the UMAT subroutine is saved. Here I select the UMAT subroutine. Then click on Submit. Now the analysis is completed. We click on the results and here we go. Here you can see all the state variables. If you remember, state variable 1 was the damage in the fibers. And the value of 0 means that no damage occurred in the fibers. Also, state variable 2 indicates the damage in the matrix. And the value of 0 means that no damage occurred in the matrix as well. State variable 3 indicates the damage in fibers under tensile loading. And it makes sense that this value is equal to 0 because the loading in this analysis is compressive. State variable 4 indicates the damage initiation in fibers under compressive loading. And these values show that the damage has started in the fibers. State variable 5 is also failure in the matrix. And these values show that composite matrices are damaged under compressive load. I hope you have got enough information, but don't worry at all. If you have any questions about this tutorial, ask us via support@caeassistant.com.